In this section, we're going to see the drain solution of in-situ stresses and change of horizontal stress due to change of pore pressure as derived from the theory of linear pore elasticity. Imagine this block of the Earth, which has a wellbore and for which we would like to answer the following questions. First, what is the state of stress, or what are the stresses in situ? And in some cases, we may have tectonic strains which are equal to 0. According to this schematic, that would be epsilon 2,2 and epsilon 1,1 equal to 0. We may have some other cases in which the tectonic stresses or strains are different than 0, and those tectonic strains then now are going may be different with respect to each other and may be also different than 0. So those two first questions relate to what is the state of stress in situ accounting for pore elasticity. The third question that we're going to answer is what is the change of the state of stress with change in pore pressure. And the fourth thing that we're going to do in this lecture is to extend 1213 to vertical transverse isotropy. And that will be a BTI rock. Okay, let's start with question number 1. What are the stresses in situ? In order to do that, what we're going to do is to use the same equations that we have used before, but now corrected by pore elasticity. We know that effective stress depends on the stiffness matrix and that multiplied to the strain tensor, right? But now we know that, let me put here number 1, now we know that effective stress has to be corrected by the BO coefficient. So in this case, effective stress is total stress minus the correction of the BO coefficient multiplied times pore pressure and multiply just the elements in the diagonal. All right, and let me here change the equation and use the alternative equation, and instead of getting stress as a function of strain, I'm going to use the equation that relates the strain as a function of the stress through the compliance matrix. But it is the same thing. And that equation looks more or less like this. We have epsilon 1,1, epsilon 2,2, epsilon 3,3, the volumetric linear strains along directions 1, 2, and 3, the shear strains, and according to the linear isotropic model, the compliance matrix looks like this. And let me separate here these submatrices and complete here writing my other vector on the right. And all right, so I know this is going to be 1 over E, 1 over E, and these matrix are going to be zeros. Let me complete here the off diagonal terms, and I know that here I'm going to have 1 over G, where G is a function of the Young modulus and the Poisson ratio, and these are zeros. And the stresses, now I'm going to use the effective stress given by the BO equation. So actually, let me make this a little bit wider because I'm going to need that space. Sigma 11 is going to be equal to S11 minus alpha times the pore pressure. S22 or sigma 22 is going to be S22 minus alpha times the pore pressure, and the same for the stress in direction 3. Are shear stresses modified by the pore pressure? No. So here I can just write directly S23, S13, and S12. Okay, let's apply now our boundary conditions that we usually apply for a medium under a passive tectonic environment. Those are that the horizontal strains are 0, and with those conditions, epsilon 11 is equal to epsilon 22, and those two are equal to 0. That will mean that these two will disappear and will be equal to 0. Also, all the shear strains are equal to 0. And I can make also those disappear. And the shear stresses are also going to be 0. So I'm going to have horizontal stresses, though, that are not 0. And let's see what we get now from these equations. For example, from the first line, if epsilon 11 is equal to 0, that means that also has to be equal to the product of the first row times the column, right? And taking advantage here of symmetry, I also know that since these two strains are 0, S11 has to be equal to S22. For reasons that are going to become a little bit more evident later, let me work with direction 2, and that's why I also made my plot like that. So S11 is going to be equal to S22, and that means that from here I'm going to be able to write well, let me write now the full equation so it's clearer. It's just a product of the first row times the vector. This is the first element. This one is the second. And finally, the third is this one. Okay. But from these conditions also we know that S11 is equal to S22. So using these equations, I can now use this as a common factor, and this is going to be actually 1 minus Poisson ratio divided Young modulus times S22 minus alpha pp, and where S11 is equal to S22 is going to be equal to Poisson ratio divided Young modulus times S33 minus alpha pp. And notice that I have the Young modulus in both sides, so I can get rid of those, and I can write now that S22 minus alpha pp is equal to Poisson ratio divided 1 minus Poisson ratio S33 minus alpha pp. Okay, this is an equation that you already know. If you remember, this is what will be the effective vertical stress, effective horizontal stress, I'm sorry, and this will be the effective vertical stress. And what is in here is the horizontal stress, effective horizontal stress coefficient, Poisson ratio divided 1 minus Poisson ratio. And we already knew this equation, but now we're going to write it a little bit differently so we can see how we can write the total stress as a function of pore pressure and the overburden. Okay, so just taking out now the total stress S22 from here, this is going to be equal to S22 is going to be equal to alpha, let me improve that alpha times the pore pressure, so I'm just moving this one to the right hand side, plus Poisson ratio 1 minus Poisson ratio times S33 minus alpha pp. And in this case, S11 is also going to be the same. Okay, I could use alpha and pore pressure and also join it with this first term, but I'm going to do that later. What I'd like to do now is to use this equation in order to write just a horizontal total stress as a function of pore pressure and the total vertical stress. And to here, getting to here, we have already solved problem number 1. What is the stress in situ, effective and total, in a tectonic environment setting? So it's this will be directly, in this case, SH mean or SH max, which are the same, so there is actually no reason to call it SH min or SH max because they are the same in a tectonically passive environment. And this is the equation that you need, right? Where instead of S33, then you will just use the vertical stress. So this one is SB. All right, so let me save some time and just go ahead and write this equation for the stresses in situ whenever the tectonic strains in direction 1 and direction 2 are not zero. It's just an extension of the same problem, but in this case, these two terms are not going to be zero. And since they are not zero, they are not going to cancel out anymore, but it's exactly the same math that I did recently in this problem, but now you just have to expand it through these terms not being equal to zero. And the solution to that is going to look similar to what I found before, but with the terms that now include the tectonic strains. And this is going to be more or less like this. And you will see a resemblance with the equations that I just wrote. SH min, SH max, SV. And SH min is going to be alpha times the pore pressure plus the contribution of the effective vertical stress. Notice that so far is the same as what I have on the equation above, but now I have to add the component of the tectonic strains, where this is going to be proportional to what is known as the plane strain modulus, and this is going to be times the, in this case, the tectonic strain in the minimum horizontal stress direction times the Poisson ratio, the tectonic strain in the maximum tectonic stress direction. SH max, very similar, is going to be like this. It's the same for the contribution of the pressure and the contribution of the effective vertical stress. But here, these terms change and the Poisson ratio switches position. Now it goes with the tectonic strain epsilon h min, and it goes fully multiplied by 1 for epsilon h max. And where SV, we know how to calculate that, is the summation of all the weight of the rock from the surface to the point that we are considering. Okay, so this is the solution now for the in situ state of stress, considering pore elasticity. You can see the BO coefficient there, and also tectonic strains. This is a drain problem because usually when these tectonic strains are applied, they have enough time to let the pressure in reservoirs or in rock formations to dissipate, so there is no undrained loading. There are some cases though in which you do have undrained loading due to tectonic strains. But let's not get into that case right now. Let's consider the drain problem. And in general, for more or less permeable formations, what you would expect is that you do not have excess pore pressure due to tectonic strain loading or to overburden pressure loading. In that case, within these formations, you can apply these equations of a drain problem and predict what are the stresses, horizontal and vertical, as a function of the pore pressure, the total vertical stress, and the tectonic strains. All right, so we have now solved problem number 2. Before going into the extension to anisotropy, let's solve problem number 3. And this is a very interesting problem. In problem number 3 now, what we're going to do is we are going to calculate what are the stresses caused by a change of pore pressure only in this formation. As a result of drawdown, we may expect a change of pressure, which is going to be negative, which means we're going to lower the pore pressure in this formation. As a result of lowering the pore pressure, what we might expect is that the effective stress is also going to change. But how much? That's a question. And before answering that, let me answer first what's going to happen with the overburden. If I change the pore pressure in this formation, would the overburden change? Do you see any reason for the overburden changing? And the answer is that probably no, because the weight of all of the rock is not going to change much after I change the pressure in the reservoir layer. The overburden is going to stay constant as long as I do not develop any arching effects on top. This cap rock is relatively soft, so that it accompanies the deformation that is going to occur when I lower the pore pressure. So if I lower the pore pressure and the overburden stays constant, that means that the effective vertical stress is going to increase. And as a result of an increase in effective vertical stress, what I'm going to have is a compaction of this reservoir layer. In this particular example, we're assuming that the entire reservoir, or at least this entire block, has suffered the same change of pore pressure. And that's relatively a good assumption when you have a very permeable formation. All right, and as a result of the pore pressure, then I'm going to have this compaction, and whatever was, for example, over here before is going to compact and is going to go into a new volume and is going to have a change of length which is proportional to that compaction. Okay, it's pretty evident that the formation is going to compact and that also the vertical effective stress is going to increase. But what about the horizontal stress? What do you think is going to happen to the effective horizontal stress and to the total horizontal stress? Well, there is no a straightforward answer to that, and that's why we're going to need to use our theory to predict that. So let me hold on this example or on this plot right now, and I'll come back with the consequences of depletion. So what we're going to do is we're going to change the pore pressure, and our objective is going to be to derive what is going to be the change of horizontal stress. Okay, so in order to do that, what I'm going to do is I'm going to use the equations that I found before, particularly this one, and this is going to be the solution to my question number 3, in which S22, or the horizontal stress, and let's keep it now for the case of the tectonically passive environment, just to make it easier, but it's going to be the same with the other one, is going to be equal to this equation that we see over here. But now let me put the two terms of the pore pressure together. So the term of the total vertical stress is going to be this one. Let me delete the parentheses. We don't need the parentheses here. And the term with the BO coefficient and the pore pressure, now notice that the common factor is going to be pore pressure. And after doing a little bit of math, I need to consider also this Poisson ratio. The result is going to be this. Here I'm going to have alpha, and I'm going to have a factor that depends on the Poisson ratio. Okay, well, now with this equation, I can discriminate the influences of both the overburden stress and the pore pressure, where, let's remind ourselves, this is the total horizontal stress. This is the contribution to horizontal stress from total vertical stress, and here we are going to call all of these a coefficient with the letter A, and this is our pore pressure. All right, so what we're going to do now is to this equation that we have over here, we're going to analyze what is the change of total horizontal stress with change of pore pressure. And mathematically, that's going to be equal to the partial derivative of S22 with respect to pore pressure. If you notice, the overburden S33 is not a function of pore pressure, at least not of the pore pressure of the formation that we are considering in this case. So let's come back to our plot. It doesn't matter if I change the pore pressure here, still the weight of the rock on top is going to be the same. So S33 is not going to be a function of pore pressure, and the Poisson ratio also, we're assuming those constant parameters, material parameters, that's not going to be a function of pore pressure. So the only thing which is actually a function of pore pressure in here is this, and the derivative of that is this parameter that we have called A. And what this tells me is that the proportionality between the change of total horizontal stress and the change of pore pressure depends on the BL coefficient and depends on the Poisson ratio. And in order to better illustrate this concept, let's plot the stresses and pore pressure as a function of time. And in this case, what I'm going to have is, for example, as a function of time, we are going to have, let's say, a constant vertical stress, S33, which in our example is SV. And here, in these conditions, the pore pressure, let's say it is somewhere over here, and is going to decrease with time. As a result, and according to these equations, what I'm going to have is that if I plot now here total stress on the y-axis and pore pressure in the x-axis, and let's say that I start at a point somewhere over here, as I decrease the pore pressure, the total vertical stress is not going to change. So this is going to be a flat line. But as I change the pore pressure, the total horizontal stress, it is going to change. And it is going to change proportionally to this parameter A. So let's assume that we have a starting total horizontal stress S22, which is somewhere around here. This is S22 at the beginning. And as I lower the pore pressure, then what this equation is telling me is that the total horizontal stress is going to decrease. And the proportionality coefficient with pore pressure is going to be this parameter A. Okay. What this equation now is telling us is that let me rewind a little bit. I forgot to say that what is the value of A. We know the Biot coefficient is positive. We know that the Poisson ratio is positive. So this parameter A is actually going to be a positive number, which means that lowering the pore pressure is going to lower the total horizontal stress. And let me hold on what that parameter A exactly is, but the fact that this A is positive, it means that I'm going to have a decrease of total stress with decrease of pore pressure. And this is a result which is quite important, because it's telling you that your total horizontal stress is going to decrease as you lower the pore pressure. And in practical applications, what that means is that, for example, if I were to do a wellbore in another location, like for example over here, when I do this wellbore, the fracture gradient or the horizontal stress that I'm going to face when going through this formation is going to be lower than what it was originally. Why? Because now my pore pressure is lower, and I saw that the result of these equations from pore elasticity also tell me that the total horizontal stress should be lower. And because of that, the tendency to have a hydraulic fracture, or the pressure needed to have a hydraulic fracture in this place, is going to be lower than before. So let me add, for example, this here, let's say 10 years later. And if I drill a wellbore 10 years later, or enough to lower the pore pressure from this reservoir, this is what I'm going to see. You could also take this example to unconventionals. After depleting a formation, and if you want to do what is called refracturing, the new pressure that you are going to use in order to fracture that formation is going to be lower than what you needed before. How much lower? It depends on all these parameters that we are seeing right now. Okay, then total horizontal stress is going to decrease with time, and this is what we see in this equation. So let's talk a little bit more in detail about what this parameter A is. And let me make here, let me find my screen. I lost it. Okay, right here. The parameter A, as we saw in this equation, is a function of the BO coefficient and the Poisson ratio. Let me save some space here, and I'm just going to plot it here. I could plot, for example, A as a function of the BO coefficient, where we know the maximum is 1, for different Poisson ratios. And for example, if the Poisson ratio were to be equal to 0, and then this will be 1/1, and if, since alpha is already equal to 1, A is going to be equal to 1. So that's going to be a point over there. And such curve will look like this. So this will be for Poisson ratio equal to 0. What does it mean, Poisson ratio equal to 0? That means a rock that does not expand laterally when you add an effective vertical stress on it. And notice that what that also means is that the change of horizontal stress, of total horizontal stress in such formation due to change of pore pressure is going to be 0. And actually pore pressure is not going to affect the total horizontal stress if the Poisson ratio is equal to 0, which is unreal, okay? But just to figure out what's going on, that means that the rock is not expanding laterally when you compact it more and more, and it makes sense that the total horizontal stress is not going to change. And for example, for a more typical Poisson ratio like 0.25, if Poisson ratio is 0.25 and let's say BO coefficient still is equal to 1, then this is going to be 0.5 divided 0.75, and that's equal to 0.66666 periodic. And so here this case is 1, and let's say for example this case is 0.5. So if I have a Poisson ratio equal to 0.25, I'm sorry, the result is going to be somewhere over there, and 0.67, and this will be the value for a Poisson ratio equal to 0.25. And as you increase the Poisson ratio, then this value of A is going to decrease. But in general, for real rocks with a Poisson ratio which is usually larger than, we know it's larger than the porosity, but also larger than more or less 0.3, 0.4, depending how tight is the rock, is going to be somewhere around this region, and with a real Poisson ratio coefficient is going to be about in the neighborhood of more or less 0.5, 0.6, 0.7. At least that's what the theory of linear pore elasticity for isotropic rocks predicts. Okay, so this parameter A is going to be important because it's going to tell me again how fast these horizontal stresses decrease with the change in pore pressure. And depending on the value of A, we saw that in some cases I could have a little change, And sometimes I could have an intermediate change like the one I have here in red. Let me actually change the color here. This will be the stress path for a different A. And there are some other cases in which apparently this change can be quite fast. Quite fast so that sometimes you can run into what we're going to see is the limit for shear yield. Okay, this may be a little bit difficult now to conceptualize, but we're going to appeal to the help of the effective stresses in order to understand what's going on here. What you should get from this plot and from this parameter is that the parameter A controls how much total stress decreases with the decrease of pore pressure, and that depends on the poroelastic properties of the rock. Okay, we answered what was the change of horizontal stress with pressure. Let's now answer what's going to be the change of effective stress with the change in pore pressure. And let me make a marker here so I can scroll down more easily. And all right, so let me come back over here. In order to do that, what I'm going to have to do now is to see what is the change of effective stress with the change of pore pressure. And for that, the equation that I need is the one that relates the change of effective stress with pore pressure. And the result is going to be the following. So let's draw a Mohr circle. For a Mohr circle, I have shear stress on the y-axis, effective normal stress on the x-axis. Let's say that I have some initial conditions in which the effective horizontal stress in direction 2 is somewhere over here. And let's keep this now to 2 dimensions. And let's say that the effective vertical stress at initial conditions is somewhere over here. At the initial state of stress, I can draw my Mohr circle. And what the theory now pore elasticity predicts is that sigma 33 is going to be equal to S33 minus alpha pp. If I change pore pressure, the change of that is going to be just negative alpha, the partial derivative. S33 doesn't change, pp is the variable, so that is negative alpha. What that means is that when I apply a change of pore pressure, sigma 33 is going to move an amount negative alpha times pp. And if I have a negative change of pressure, that means the pressure is lower in the final point, then negative times negative is going to be positive, and the change of effective horizontal stress, the change of effective vertical stress, sigma 33, is going to be positive. And the new position is going to be somewhere over here, where the distance between these 2 points is alpha times the change of pore pressure. That's for the new effective vertical stress. For the effective horizontal stress, now I have to use this equation that I have over here, and when I take the derivative of sigma 22 with a change of the pore pressure, the only thing that is going to survive out of here is going to be alpha times Poisson ratio divided 1 minus Poisson ratio. And just for the sake of convenience, I can also use the definition of the parameter A, and after doing some math, the result is going to be from those two equations that the change of the effective horizontal stress with change of pore pressure is going to be negative alpha minus A, and this change is going to be equal to, is also going to be an increase. Notice that alpha is going to be larger than A, so this is going to be an increase, and it's going to be an increase which is going to be smaller than the one I had before. And this is going to be equal to, as we said before, alpha, the distance is going to be alpha minus A times delta pp. And the new point is going to be somewhere over here. The equations tell me that the effective horizontal stress is going to increase. We saw before that the total horizontal stress is going to decrease. But remember that the effective horizontal stress is going to increase. And the new Mohr circle, therefore, is going to move to the right. But not only that, it's also going to increase in size, because the effective vertical stress has moved more than the effective horizontal stress. And as a result of that, since this one is lagging compared to this one, the net result is going to be that my Mohr circle with time is moving into this direction. And let's now add to these plots a component of shear failure. Let's say that I have a shear failure in my material which is, let me do it somewhere over here. This is my equation of the shear failure or shear yield, and depending on what is the value of alpha and the Poisson ratio, the steeper is this path into the shear yield, that means that I might get into shear failure within the reservoir because of the change of pore pressure. And that explains what we saw before over here. It was not that easy to see, but now we see it more clearly with the Mohr circle. So if I have a path that goes more into the shear yield, that's going to cause shear failure within this depleted formation. If I have a path that goes more like goes flatter in this direction, what I'm going to do is I'm going to run into this other limit, which is the limit for compaction yield or compaction plastic strains, which means that by decreasing the pore pressure, I might get into a region of plastic deformations for this reservoir. Okay, this is when you get to the compaction yield, is when you get into significant volumetric strain, significant losses of porosity, significant subsidence, and problems with casing shearing on top, or casing buckling in the reservoir, and that is something we're going to talk a little bit more about in a bit. But let me come back to this important point in which we said that the effective horizontal stress is going to increase. The implications for that are that, for example, if in this formation, to begin with, I had a naturally fractured formation, as the effective stress increases in this formation due to the decreasing pore pressure, these fractures are going to start to close. Why? Because I have more effective horizontal stress. And the same, for example, if I were to do a hydraulic fracture in this case, as I start to deplete, the horizontal, or in this case, the hydraulic fractures are going to start to close. If those hydraulic fractures are propped with a proppant, and the effective stress is too high, that proppant may start to get embedded, and the flow rates are going to start to decrease. If I want to predict all of those consequences, I need to take into account that increase of effective stress with depletion, which is predicted by this equation. And just let me complete this equation with what we had on top over here. So if I take the derivative of this equation with respect to pore pressure, then the only thing that's going to survive is negative Biot coefficient times the effective stress ratio. And we know that this is less than 1. Okay. The same thing that we have done for the passive tectonic environment, it actually also works for the active tectonic environment, because these strains over here, they are not going to change over a few years what it takes for the depletion to happen. So when I take derivatives or partial derivatives with respect to pore pressure, these also are not going to get into the picture. So actually the equations that then we just calculated, they are valid for both a tectonically passive and a tectonically active environment. Before I go to the next topic, and with which we're going to finish this lecture, let me share with you some real data of change of horizontal stress with change of pore pressure. And this is what you see in this plot here on the left. This is a paper. Here is the name, authored by Golti, reservoir stress path during depletion of Norwegian chalk oil fields. And what we can see is that, as we said, as pressure decreases because of depletion, minimum horizontal stress decrease. How did they measure in this case this minimum horizontal stress change? With hydraulic fracturing test, in this case a leak-off test, that allowed to see how pressure changed due, the minimum horizontal stress changed due to the change in pore pressure. Also, you can see what is the value in the field for this parameter A, which in this case turned out to be a little bit higher than what we saw for pore elasticity. In the case of the chalk, it's a very soft material and the Biot coefficient would tend to be very high. So those values would be somewhere around here. And what it's measured in the field, it's more or less a value that goes from 0.77, as you see, from 0.84. But again, this is just a proof that this actually happens in the field. Okay, so we have answered question number 1, state of stress in situ for a passive environment. Question number 2, stresses in situ for an active tectonic environment. Question number 3, the change of stresses due to the change in pore pressure. Let me mention also this is a drain problem, because we are assuming that the pore pressure has equilibrated in the reservoir such that it's not causing more elastic strains in the matrix due to undrained loading. So, and this would apply for very permeable formations. And let's go to number 4, which is extend this to a vertical transverse isotropic rock. Well, we're not going to go through the entire derivation because that's going to take quite a while. But the principle is exactly the same to what we have applied before. First, we write the stiffness, in this case, a compliance matrix, and we relate those strains to those stresses. And let me bring that equation to you. I have actually typed this recently into my latex notes, and it is right here. Okay, so let me bring it from my other monitor into this one. The equivalent of the equation that we see over here, the compliance matrix for a BTI material, is the one that I have over here. And this equation then is the one that I'm going to use in order to derive my equations for pore elasticity, but now for a BTI material. Okay, so basically then we're going to do exactly the same procedure that we did before, but now we're going to do it with the material properties which are anisotropic, but it is exactly the same thing. And let me paste this into here. And the result is going to be the following. Let me make some space. SH mean is going to be equal to alpha H times the pore pressure plus a function of the Poisson ratios. I'm going to explain in a minute what these are, but let me bring the question on the top. So here you see we have horizontal Young moduli, vertical Young moduli, horizontal Poisson ratios, and vertical Poisson ratios, and that's the ones I'm using now in this equation. It's very similar to the one that we had before, but now you can notice the influence of the anisotropic parameters and where they go into the equations. For example, notice here that the plane strain modulus refers just to the horizontal stiffness, and that makes a lot of sense. And the tectonic strains are amplified by the horizontal Poisson ratio, and that also makes a lot of sense. So this should be, this is epsilon H mean. And the next equation is pretty similar. And this part is exactly the same as the one before. By the way, if you want to do this derivation, it takes about 2 pages, and it's not too long, but it's definitely doable in less than half an hour. Okay, so now new H goes with this one, and this is epsilon H max, and we know that SV is the summation of the weight of the rock above the point I am considering. And just for the sake of also completing this, effective vertical stress is SV minus alpha V P P. All right, so these are the equations for the VTI model. We already know what is the vertical Young modulus, the horizontal Young modulus, horizontal and vertical Poisson ratios. This is something that has been covered before in the lecture or vertical transverse isotropic materials. And here we see new coefficients that we didn't see before. And those are alpha H and alpha V. So also for the sake of completeness, actually, let me write here that sigma H mean is going to be SH mean minus alpha H pore pressure, sigma H max is SH max minus alpha H pore pressure, and let me move this equation over here so it looks consistent to what I have underneath. Okay, come on. All right. Okay. Well, this is sigma V, and now you may be asking yourself, what are those new parameters that we see, alpha H and alpha V? Well, doing similar derivations to what we did for the poroelastic isotropic solid, we can extend this to the VTI solid for pore elasticity and show that alpha H is going to have an equation similar to the one for the isotropic solid, but now I need to use the stiffness parameters from the stiffness matrix. And if you derive these equations, you will find that this is the equation for alpha H, where C11, C12, C13 apply to the porous solid, or those are the bulk stiffnesses of the porous solid, and Ks is the, let's actually use M, Km is the stiffness bulk modulus of the matrix. Alpha V is similar to this, but now I have parameters C13 and C33 divided 3 km, and an equation that these two you may find it in many papers, but let me fix this K, doesn't look like a K. The one that you probably may not find is the one of the pore modulus N, and the pore modulus N is going to be equal to 2 alpha 1 plus this is actually alpha H, 2 alpha H plus alpha V divided by 3 minus the initial porosity divided the bulk modulus of the matrix. So you see that it's similar to the one of the isotropic solid, it's just an average of that. And now you have basically everything that you need in order to build an isotropic poroelastic model of the subsurface. If you also wanted to predict changes of stress with changes of pore pressure, you can do that. Here you have the full equations. You will just have to take those partial derivatives with respect to the particular, in this case, to pressure. That's the variable that you are changing. And with this type of derivation is that, for example, we arrive to the model that we work with in the first class, in which this model, if you go to the paper, you will see that uses an anisotropic poroelastic model in order to predict the horizontal stresses as a function of depth for this particular shale in the south of South America. All right, so with this we finish this lecture, and in the next lecture we're going to start talking about problems of undrained pore elasticity.